Hello Western, and welcome to the first AP Physics B video lecture. In this lecture, I'm going to introduce the concept of units and talk about several different types of systems of units that are used. Now, before I start talking about units, I want to briefly just discuss what physics actually is. Basically, physics is an area of science which attempts to describe absolutely everything that we see. Physics is sometimes referred to as a fundamental science. And what this means is that the laws and equations that we discover in physics are supposed to apply in absolutely any situation. In fact, if a law only applies in a very narrow situation, we would consider this to be a failure. Now, one of the consequences of this is that at the beginning of the year, when we talk about something like Newton's laws, this law will continue to carry throughout the year and it will continue to apply. So later on in the year, when we talk about the work-energy theorem and the impulse-momentum theorem, we'll actually be able to show that both of these things derive directly from Newton's laws. Even when we talk about a very specific phenomenon, like fluids, and we talk about something like Bernoulli's equation, which describes how the pressure inside a pipe changes, we'll see that this is in fact nothing more than the work-energy theorem rewritten in terms of variables that describe fluids. Now, this doesn't mean that everything that we talk about can be derived from Newton's laws. For example, when we talk about charged particles, we'll introduce another law called Coulomb's law. And Coulomb's law cannot be derived from Newton's law. This is something that was discovered through experimentation. But nonetheless, Newton's law still applies to charged particles. And because Newton's laws apply to charged particles, the impulse-momentum theorem and the work-energy theorem also apply. Now, one of the things that physics has in common with other areas of science is that physics is an empirical science. What this means is that everything that we've learned about physics comes from experimentation and observation. Because of this, we need to have some kind of systematic way of describing the observations that we see. One of the most fruitful ways that we found to describe our observations is by quantifying observable properties. This has two major advantages. The first is it allows us to very precisely describe an observation. The second is that it allows us to discuss the relationship between different types of properties using mathematics. As the Franciscan friar Roger Bacon once said, "If in other sciences we should arrive at certainty without doubt and truth without error, it behooves us to place the foundations of knowledge in mathematics." And this is exactly what we do in physics. So how do we quantify our observations? What we do is we create a metric or a unit that we use to measure other things. So for example, we have the inch to measure units of length. There's feet, centimeters, and meters. These are all units that we can use to measure lengths. So I could talk about something as being 1 inch long or 2 inches long, for example. Now, whenever we try to describe an observation, most of the time we'll need to use more than just one type of unit. So for example, if I want to talk about how fast something's moving, I'll need to talk about distance to describe how its position is changing, but I'll also need time to describe how quickly the position is changing. Any collection of units is called a system of units. The most common system of units that are used, and the one that we're going to use in this class, is called the SI, which stands for the International System, which I think is French for something. So here in this table, I'm just summarizing the SI units. So we have the kilogram as a unit of mass, the meter as a unit of distance, and the second is a unit of time. In addition to these, there's the ampere, Kelvin, and mole. Hopefully these last two are familiar from your chemistry classes. One of the major advantages to using a metric-based system is that the metric system is decimal-based. This means that it's based on factors of 10. So there are other units in the metric system. Each one of these differ from a base unit by a factor of 1,000. And there's also a simple naming convention for these different types of units. You just take the prefix and tack it in front of the unit. So for example, if I wanted to talk about distances between cities, because this type of distance is usually on the order of thousands of meters, I might measure the distance between cities using kilometers. So I just take the prefix kilo and put it in front of meter. We have a kilometer. And that is equal to 1,000 meters. Or using the abbreviation, we have 1 kilometer is 10 to the third meters. In addition to the SI, there are other systems of units. In the United States, the most commonly used units are the imperial units, where we have the inch, the foot, and the mile are all units of length. We have the pound, which is a unit of force, the slug, which is a unit of mass, and the second, which is a unit of time. The most commonly used system in the United States is the foot-pound-second system, or the FPS system. Additionally, there are other systems of units, like the CGS system, which stands for the centimeter, gram, and second system. This is a system that's used in chemistry and astronomy. There's also something called a natural system of units. This is a system of units that is used in computational physics, so that's an area of physics where we try to solve really complicated problems using computers. Natural units are a system of units that are very specific to a particular problem. These units are chosen so that most quantities have a numeric value of approximately 1. So for example, if I wanted to come up with a system of units that describe the Earth's orbit around the Sun, I would choose my unit for distance as being the distance between the Earth and the Sun, which is also called an astronomical unit. And I might choose my unit of time to be a year, since that's the amount of time it takes for the Earth to orbit the Sun. Now, the mass is a little bit trickier, because of course the Sun and the Earth have vastly different masses. The typical way that we handle this is we set the universal gravitational constant, big G, to have a numeric value of approximately 1. Now, all of the units that we've talked about up until now are what are called base units. These are units which are just arbitrarily defined with regard to some kind of reference. Now, throughout the year, we're going to discover various combinations of units have very specific properties and are very useful. For example, when we talk about force, we see that the units of force have units of kilograms, meters per second squared. And because we're constantly talking about force all the time, and because force has a very important meaning in physics, we take this collection of units and we simply call these newtons. So a newton is an example of a unit which is defined in terms of base units, and this is called a derived unit. And so here in this table, I just have several different derived units. So we can see the newton, the joule, watt, the pascal, and the hertz. And all of these are units which are measured in terms of kilograms, meters, and seconds. So I think I'd like to end the lecture there. And in the next lecture, I'm going to talk about how we convert between different types of units.